All right, we have already talked about conservation of energy, and in our previous conversation, we just went over the main idea that energy is not created nor destroyed, it's just simply transformed into different forms of energy. And so right now what we're doing is we are talking about mechanical energy in terms of gravitational potential energy and kinetic energy, and we are saying that we can show conservation of mechanical energy by simply taking the idea that those two values are always going to add up for our total so that all of our energy is accounted for. When we have a frictionless system, we're going to see true conservation of energy. So what we originally had on the slide here was 50 joules of energy is accounted for at all locations on a roller coaster. But then we added the statement here in red. If we have a situation where friction is being considered, now we need to understand that friction produces heat, which is a type of energy, and so we would have something less than our original total by the time we are done with our situation, because that energy is being transformed into thermal energy, which is not part of our mechanical, gravitational potential and kinetic energy form. So what we're going to do now is we're going to work through some problems where we are continuing that same main idea. So here we have a ball, and we're told in the story that it has a mass of 0.55 kilograms. And it is located on a frictionless ramp that is 7.5 meters above the ground. It says that it begins from rest. And then they want to know how much kinetic energy will the ball have when it reaches the ground. So you can see here that I have identified my givens not only as mass, height, velocity, but I've also given them a specific initial or final notation. So when we're talking about conservation of energy, remember it's the transition from here to there, and it's connecting those two locations, or the energy at those two locations. It's going to allow me to be able to actually calculate whatever variable I am supposed to be solving for. So when we look at a conservation question, if we give you a picture, I would highly recommend that you simply write the notations on the picture, just like I'm about to show you. If you do not have a picture, at minimum, I want you to at least mentally think about what we're about to do, okay? So what I want you to do at each location is I want you to say yes or no, I have potential energy. Yes or no, I have kinetic energy. Because our ability to simply recognize that we do or do not have energy is going to be part of how we piece together our conservation relationship. That's ultimately going to guide my math work for me to solve the question. At the absolute highest point, we say that kinetic energy is 0. Now, in this question, they gave me an initial velocity of 0, so I could technically calculate this out, and I'd calculate 0. But conceptually, we said at the absolute highest physical position that this object can obtain, the top of the ramp is the highest we can get, kinetic energy is 0. So we're all potential, and then we get to the ground, we obviously have a height of 0, so we don't have any potential energy there. Now we are all kinetic because that total is always conserved. So what we're going to do for this question is we're going to need to figure out how much potential energy do we have at the highest point of the ramp, and then when my object gets to the bottom of the ramp, so by the time we get down here, it's going to be the same amount of kinetic energy. Now, most students would prefer to say that they are going to use their potential energy equation. They're going to plug their numbers in, they're going to get their potential energy, and then they're just going to copy that down as the answer for their kinetic energy. And there is absolutely nothing wrong with that. But the idea here is that we are showing conservation. So what I'm going to do is I'm going to show you what this equation should look like if we are actually using that conservation relationship. So my initial potential and kinetic energy is going to give me the same total as my final potential and kinetic energy. So as you can see in the picture, we have already identified that my kinetic energy is 0. So this part of my equation is going to go away because I'm adding nothing. Down here at the bottom of the ramp, my potential energy is the one that is 0. So I'm going to simplify this equation by saying potential energy, which is mass times gravity times height, and that's going to be initially, so in this case at the top of the ramp, is equal to the final kinetic energy, which in this case is at the bottom of the ramp. And so now I'm going to plug in my numbers, 0.55 times 9.8 times 7.5, and that is going to tell me how much energy I have initially at the top of the ramp, which is the same value that I will have at the bottom of the ramp, but now it's going to be in the form of kinetic energy. So most students would choose to make this a two-step problem where they solve one and then just simply slide it over to the other. But I really want you guys to get comfortable with the idea of putting everything together in this conservation form. In most of the questions, doing it as a two-step problem is absolutely going to be doable, and it will give you the correct final answer. But there is a small percentage of circumstances where you won't know enough information for you to be able to calculate one and then go in and calculate the other. But if you put it into the conservation formula and simply just fill in all of the parts as needed, you'll find that you are still able to finish that calculation simply because you truly use the conservation idea and that conservation equation. So something to keep in mind for future questions. All right, so now we are looking at a pendulum, and the pendulum is being raised. It is 3 kilograms in mass, and it says that we're going to pull it so that it's a distance of 2 meters above the ground. So I am going to choose to list this as a height because it's a vertical position. You can choose to list it as a distance or displacement. Just make sure you recognize that it is a vertical displacement. And then it says that they want us to calculate the maximum speed that the pendulum is going to have after it is released. So a few things, just kind of big picture main idea. Number one, we're going to say yes, no to each energy. So potential energy here, yes. How do I know that? Because I have a height, so I have some potential energy. Kinetic energy here, that's going to be a no. So conceptually, this is the highest possible position. We are raising it to this height, and then we are going to let go. So at the highest point, velocity is 0, therefore kinetic energy is 0. Number 2, at this position, we are going to say potential energy is a no. Now here, we identified as potential energy as being gravitational potential energy, where it is the vertical displacement above what we're going to call ground level. That's going to determine how high the object is and what that energy ends up being. So if we are to analyze this situation, my object will never physically be on the ground because it's on a string, and this is the lowest possible physical position. So this becomes my ground level. So here I have a height of 0, which is why potential energy is 0. And if I go back and read the question or look at the picture, they're trying to illustrate to me that the 2 meters is being measured from this location. So again, emphasizing that this is our ground level or the height of 0. So once we've acknowledged that, now it should be clear. Potential energy is 0. Kinetic energy will be a yes. We are to assume that my object is moving at this location. In fact, this is the lowest possible position. And so again, main idea, the lowest possible position is where we're going to have the greatest amount of kinetic energy. So even if this question wasn't about an object on the ground, if this is the lowest of the positions we are analyzing, it's going to have the greatest speed. Therefore, it's going to have the greatest kinetic energy. So when it's asking me in the question for the maximum speed, they are asking for the velocity at this location. So now, once again, conceptually speaking, a lot of students would choose to calculate the potential energy here by using the potential energy formula. Then they're going to take that number, they're going to slide it over as their kinetic energy here, and then they're going to use the kinetic energy equation in order to figure out what that velocity is. 95% of the time, totally not a problem. But let's go ahead and work this as a true conservation type of formula. So what we're going to take is the sum of our initial potential and kinetic energy, and we're going to add that, we're going to set that equal to the sum of our final potential and kinetic energy. So initially, kinetic energy is 0. At the end, or in this case, at the lowest possible point, my potential energy is 0. And so what I get is mass times gravity times height initially, so at that 2-meter position, is equal to 1/2 times mass times velocity squared, where this is the final velocity at the lowest point of the pendulum swing. I'm going to calculate all of the same types of information. I'm just simply setting it up, number one, so that it's only one math problem instead of 2. And secondly, I'm setting this up in a relationship that's going to work for all of the questions that we're going to give you. So now I'm going to take the numbers that I have and I'm going to plug them in. So I'm going to write 3 times 9.8 times my initial height of 2 is equal to 1/2 times 3 times my final velocity, which is written as v squared. From here, now you just need to be able to finish the algebra. Yes, I could choose to simplify this side, which if that's how you wanted to do it, this comes out to 58.8 joules. And then I would take that and I would set my 58.8 joules equal to the 1/2 3v squared, right? So that's how it would look if we did it as a 2-step problem. If I'm working this as just one big equation, I think what most students would choose to do would be to simplify the left side. They'd simplify the right side. And then from here, it's just a matter of knowing how to finish your algebra. We're going to divide both sides by 1.5. That is going to give me 39.2. And that is equal to v squared. So then the next thing I need to do is square root that. That's going to give me 6.2609 as my velocity. So I would write my final velocity here. Let's write it on this other side. I would write my final velocity as being 6.3 meters per second. Okay. So on the next picture, we're not doing any math. We're just kind of reinforcing some main ideas here. It says that we have a soccer ball, and this soccer ball is going to move down a frictionless track. The initial velocity of the ball is 0. And they want to ask us, how far will it roll, or how high will it roll over on the other side of the hill? So the ball is going to roll. How high will it get is what it's asking. So our answer here is going to be E as in elephant. The reason being, here we have established how much energy the soccer ball has and how much energy is going to be available for the entire system. So if we are at a height of 10 meters, that's going to establish how much potential energy we have. We can't roll any higher than 10 meters. So it's only going to be able to get up to position E. A lot of times students want to say F just because it's the highest point on the picture, but F would be a higher displacement, which means that it would require more energy, and we can't do that. However much energy we start with is what we have as our total for the whole system. The next question, at what point does the ball have a maximum speed? We've already reviewed that main idea. It's going to be at the lowest point. So in this picture, that's going to be point C. At what point is the kinetic energy the maximum? That's also going to be the lowest point. And so that's going to be point C. Here we have a situation where they have given us the weight of our object. And it says that the object is placed 1.5 meters high on this ramp, and we have 30 joules of energy that's going to be converted to heat as the box slides down the hill, or down the ramp, sorry. And they want me to determine what is the kinetic energy when it reaches the bottom of the ramp. So yes, no. PE, yes. KE, no. PE, no, because we would be at a height of 0 here. KE, yes. And so what we would want to do is calculate how much potential energy do we have right here. So we would take mass times gravity. Oh, wait a minute. Mass times gravity is my weight. So this is something that we've definitely discussed in previous conversations, but let's just take a moment to review. mg is how you calculate the weight of an object. So when they gave me the weight of 64, that's going to take the place of both mass and gravity in my potential energy equation. And so now I just need to multiply that by the height. And so when I do that, I get 96 joules. So at this highest point, I have 96 joules of energy. Now, typically, we would say that that means we have 96 joules at the bottom, but this question wants us to consider friction. It tells me that thermal energy is being produced. Thermal energy is not one of our mechanical energy categories, so this is not going to be a value that we're going to add to our system. This is a value that we are going to subtract from our system. So we start with 96 joules of potential energy at the top. As the box moves down the hill, 30 joules are converted into thermal energy, which means by the time we get to the bottom, 96 minus 30 equals 66. By the time we get to the bottom of the ramp, there's only 66 joules of energy available because we removed 30 due to heat. Okay, so this is our last question. What we are given here is a variety of pieces of information at different locations on the picture. So what we are being told in the initial statement is that at point A, the skier has a mass of 68 kilograms and is moving at 6.3 meters per second. So we have a mass of 68 kilograms. We have a velocity of 6.3 meters per second. And then I'm asked to identify all of the types of energy present at each location. So basically, we're saying yes, no to each type of energy on the picture. So at point A, yes, we have potential energy because we have a height. We also have a kinetic energy. Now, a lot of students want to just tell me no, probably out of habit. We are not, or my skier is not at the highest possible physical location. So that is not a kinetic energy of 0. It is not a velocity of 0. In fact, in the story, they gave me how fast the object was moving. So yes to both PE and KE, and we're going to add those up to get our total. At point B, it's yes to both. Once again, I have a height and my object will have a velocity. At point C, it's going to be PE no, KE yes, and then at point D, it's going to be both PE and KE. So just taking a moment to understand that you do or don't have both types of energy should be helpful whenever you're trying to figure out how to connect the pieces at the different locations throughout the story. Now they are asking us to calculate. So KE is equal to 1/2 mv squared. So I'm simply going to say 1/2 of my mass times the velocity at this location squared. And that gives me a value of 1,349.46 joules. My potential energy is mass times gravity times height. So I'm going to take my mass times 9.8 for the acceleration caused by gravity times a height of 12 meters at this location to get a value of 7,996.8 joules. Now, TME is one way to write total mechanical energy. And remember, mechanical energy we have classified as our gravitational potential energy plus our kinetic energy. So all I'm going to do is take these two energy values and just simply add them up in order to get my total. So once I add these two together, I get 9,346.26 joules. Okay? Now, why are the lines there? Well, you know, if we're taking a quiz or a test and I have a question A, question B, question C, they all have to individually be rounded for sig figs. Our height is going to be the limiting factor for sig figs here, and actually the velocity on that initial statement as well. So 2 sig figs for this particular set of answers. So we're going to have 1,400 joules of kinetic energy. We're going to have 8,000 joules of potential energy, which gives us 9,300 joules of energy in total. Remember, total mechanical energy does not change. So when we are trying to calculate the answers for point B, we now need to move to this location on the picture. And you can see here we have both potential and kinetic energy. So if we try to calculate our kinetic energy by using this formula, we're going to find that we can't do that because we don't have a velocity. So at this point, it's not uncommon for students to just get really frustrated. They're confused. They're like, wait a minute, I don't understand. The equation says it's mass times velocity squared. They didn't tell me the velocity. I can't solve it. Well, we can, but for right now, we're going to say, yeah, I'm not really sure what to do, so we're going to skip it and we'll come back to it. My potential energy is mass times gravity times height, and so I do have all of these values, so we're going to go ahead and plug this in. And so now at a height of 8 meters, I have a potential energy of 5,331.2 joules. Now remember, my total mechanical energy does not change, so I just automatically know this number because it's going to be the same at every place on the ski slope. So now let's go back to my kinetic energy. I know that the total mechanical energy initial is equal to the total mechanical initial energy final, which in this case would be the potential energy at point B plus the kinetic energy at point B. So I know this number is 9346.26. I have already calculated that this number is 5331.2, and that leaves me with my kinetic energy as the only value left. So I'm going to subtract the 5331.2 from both sides, and I get a value of 4,015.6 joules. So this number becomes 4,000 joules. This number is 5,300 joules, which gives me a total of 9,300 joules. Okay, now for this last little piece, I'm going to see if I can just kind of copy some of this, and let's carry it over to the next page. All right, so now we are looking at the same picture, but now we're focusing on this bottom part of the picture, or the last part of the picture, where we are at location C. So location C, I already did the legwork on just my initial analysis of the situation, and I have stated that my potential energy is 0. So I know that answer, real easy peasy. And I understand that mechanical energy is conserved, so my total value is also already known. So the only thing left to figure out here is how much kinetic energy, and remember, these two things have to add up to our total, so this has to be 9,346.26. This is a conceptual question. No math needed. Main idea tells me that these two numbers are going to always add up to the same total, and so I should just know these values right off the bat. That should be a very simple question. So now when we get to the last question, they're asking me for the velocity specifically at location C, where I have now identified that at location C, I have a kinetic energy of 9,346. So I'm simply going to use the equation for kinetic energy, and I'm going to put the value in at that particular location and set that equal to 1/2 mv squared. And then from here, it's just a matter of finishing our algebra. So just very briefly, I'm going to shortcut this one. 1/2 of 68 is 34, so I'm going to divide both sides by 34. And so this is going to give me 274.89 is equal to v squared. And then once again, I need to square root that. And so now I have 16.5798 is equal to v. So my final answer here is that the velocity at point C is 17 meters per second.